All right, so why have we been doing so much work on balancing equations? That's what we're going to take a look at today. All right, we're going to take a look at the mole. This should sound familiar. Remember the mole from Mole Day. Moles is a counting term, so we use counting terms today. For instance, we use the ream, the pair, the dozen, right? A dozen means 12. A pair always means 2. A mole. Okay, well, so how many cars are in a dozen cars? We know there's 12. Wheels are in a dozen wheels of a dozen cars. We're going to multiply 4 times a dozen and we'll get 48. How many wipers are in a dozen car? We'll multiply 2 times a dozen and get 24 wipers. We're going to do the same type of math, but with this number right here. Okay, this is the number of atoms or particles or formula units or molecules in a mole of any of those items we just mentioned. Any particles or formula units or molecules each contain 6.02 times 10 to the 23rd. So a mole is 6.022 times 10 to the 23rd particles or atoms or molecules. Depends on what we're asking. This number is called Avogadro's number, okay, named just in his honor. He didn't come up with it, but it is named in his honor. So the question is, just to think about it, how many cars would be in a mole of cars? Well, there would be 6.02 times 10 to the 23rd cars, but that would be way too many cars. They wouldn't even fit on the earth. So we don't usually use it to talk about cars, but if we said how many wheels are in a mole of cars, right? Well, there's 4 wheels on one car, so we would multiply 4 times 6.02 times 10 to the 23rd, and we would get 24 times 10 to the 23rd. How about wipers? Well, there's 2 wipers on one car, so we would multiply 2 times 6.02 times 10 to the 23rd, so we would get 12.044 times 10 to the 23rd cars, or wipers, sorry. So in a chemical reaction, we use coefficients to represent the number of moles of each element or compound in the reaction, right? So we used 4 iron. In this reaction, there'd be 4 moles of iron, 3 moles of oxygen, and 2 moles of iron 3 oxide. All right, so we're just using, again, we're using the coefficient, this number right in front of the element, this number right in front of our diatomic oxygen, this number right in front of our iron 3 oxide. But suppose we want to react iron and oxygen, and we need to know the amount of iron oxide that will be produced. So we write down our reaction, we get the correct coefficients, we balance the equation. All right, if we need 2 moles of iron oxide, then we need to react 4 moles of iron with 3 moles of oxygen. If we react 4 moles of iron, right, with 3 moles of oxygen, we will produce 2 moles of iron oxide. But suppose we want twice the amount of iron oxide. Well, if we want twice the amount, instead of 2 moles of iron oxide, if we want 4 moles of iron oxide, then we must react 8 moles of iron. We're just doubling this number. And we must react 6 moles of oxygen. Suppose we don't want a nice easy number. We want exactly 6.7 moles of iron 3 oxide. All right, we will need to use a conversion factor. Okay, just give me a second. I'm gonna get my dog. Buddy, you're fine. Oh my gosh, just leave him in. All right, that's just my dog. He's a beagle. Okay, he's fine. I just left him inside the office with me, so He doesn't keep crying. So anyway, we need a conversion factor. All right, our conversion factor looks like this. 2 moles of iron oxide is equal to 4 moles of iron. That's our conversion factor. We're going to change it into a factor in a minute. Here's our second factor. 2 moles of iron oxide is equal to 3 moles of oxygen in this reaction. Again, these ratios only refer to this reaction. If we change the reaction, we change the ratios. All right, so let's put these in a factor. All right, so now we have a ratio. This is our conversion factor that we are multiplying by. All right, so we put down, we start with, we want to produce 6.7 moles of iron 3 oxide, but we want to know how much iron we need. So we put our conversion factor next to what we start with, what it's asking, 6.7 moles of iron oxide, and we're multiplying that by the ratio. In the equation, in the reaction, 4 moles of iron is equivalent to 2 moles of iron oxide. So we put this in the equation, but we want to write it in such a way that the iron oxide cancels out, right? So we put the moles of iron oxide on the bottom, and then we put the moles of iron on the top because that is what we want to find out. All right, then we do the math. We multiply 6.7 times 4 and divide it by 2. And then we get 13.4 moles of iron. Okay, how much oxygen would be used up in the reaction? Well, we write our conversion factor right here. Okay, 2 moles of iron oxide are made from 3 moles of oxygen. We want our iron oxide to cancel out, so we need to put iron oxide on the bottom because we want to find out about the oxygen. We want to get rid of the iron oxide and find out about the oxygen, so we need to put that on the bottom. Then our moles of iron oxide cancel out, and we do the math. 6.7 times 3 divided by 2 gives us 10.05 moles of oxygen. Let's suppose we begin with 0.62 moles of iron and react it in an unlimited supply of oxygen. How much iron 3 oxide can we produce? All right, we take the same equation. We never change this balanced reaction. But we always need to use a conversion factor. All right, we want to know how the moles of iron oxide equates to the moles of iron. So that will be our conversion factor. 2 moles of iron oxide equates to 4 moles of iron in this reaction. We have an unlimited supply of oxygen, so really we are not worried about the bottom conversion factor. So what do? Well, we have 0.62 moles of iron, and we want to see how much iron oxide that will make. So we need to get rid of the iron. We need to put our conversion factor next to it with the 2 moles of iron oxide on the top, and the 4 moles of iron would go on the bottom, so that the moles of iron cancel out because one is on the top and one is on the bottom, so moles cancels out, and we do the math. 0.62 times 2 divided by 4. That will give us 0.31 moles of iron oxide. So we just produced 0.31 moles of iron oxide. Now we want to know how many formula units is that. Formula units means we're going to use Avogadro's number. Okay, so here's our balanced reaction. What's our conversion factor? It's asking for formula units. We're using Avogadro's number. 2 moles of, this is wrong. Hold up a second. What's wrong here? 1 mole is equal to 6.02 times 10 to the 23rd. So let's just fix that here. There we go. All right, 1 mole of iron oxide is equivalent to 6.02 times 10 to the 23rd formula units of iron oxide. All right, so what did we begin with? We know we have 0.31 moles of iron oxide. We want to find out how many formula units that is. In other words, how many particles of iron oxide is that? So we want to get rid of the moles. We put the moles of iron oxide on the bottom. We want to convert it to formula units of iron oxide. So we put the 6.02 times 10 to the 23rd on the top. All right, thank you, Evelyn. That's my daughter taking Buddy out so he doesn't keep crying. Okay, 0.31 moles of iron oxide and will cancel out. The moles will cancel out. We're going to keep all the numbers. So we're going to multiply 0.31 times 6.02 times 10 to the 23rd, and that will give us 1.87 times 10 to the 23rd formula units of iron oxide. So there'll be this many particles of iron oxide. If there's 0.31 moles of it, there's this many particles. All right, here's another question. If we begin with 0.62 moles of iron, what mass of iron must I weigh in the lab? All right, here's our balanced equation again, our balanced reaction. We will need to use a conversion factor from the periodic table. From the periodic table, if you look up the atomic mass, now we're going to call this the molar mass. All right, because this is the mass in the periodic table of 1 mole of iron. All right, so we are going to take our iron, our 0.62 moles of iron, and convert it to mass of iron. So you can guess what's going to go on the bottom. We will want the moles to cancel out. 0.62 moles of iron times 55.85 grams of iron in every mole. This is our equivalent factor or our conversion factor. This and this need to be equivalent. And if you look on the periodic table, they are equivalent. This is the mass of 1 mole of iron. And we want mole of iron. They need to match so we can cancel them out. So the mole of iron and this mole of iron cancel out, and we keep the numbers to do the math. 0.62 times 55.85 grams of iron. That gives us 34.6 grams of iron. So if I want 0.62 moles of iron in my reaction, then I need to measure 34.6 grams of iron. So the key to all this stoichiometry is finding the conversion factor. Stoichiometry is nothing but a bunch of conversion factors. So let's try some more conversion factors. How many copper atoms are in 0.0629 moles of a sample of pure copper wire? Well, it's asking for atoms, right? Picture tiny little atoms. How do we count atoms? We count them with Avogadro's number. All right, well, of course, we want Avogadro's number because it says how many, so that's on the top. Whenever it says how many of what, that goes on the top. Whatever we are given, we're given moles, well, that goes on the bottom because we don't want that anymore. We want to change from moles to atoms, right? So we do the math. 0.0629 times 6.022 times 10 to the 23rd. That gives us 3.79 times 10 to the 22nd atoms of copper. All right, let's take a look at another one. What is the mass of 5 moles of potassium atoms? Okay, it says, what is the mass? So we're going to put mass on the top because it's asking for the mass. We want to put the mass on the top. We are given the moles, 5 moles of potassium. So the moles of potassium in our conversion factor, in our ratio, goes on the bottom. So again, how do we know that? It's asking for mass. I want to put the mass on the top. It's telling me moles. I want to put the mole for the conversion factor on the bottom. And where do I get 39.1 grams? Well, I'm going to get this from the periodic table. If you see anything referring to mass, know that you need to use the periodic table. All right, so the moles can cancel out, and we're going to multiply 5 times 39.1 gives us 196 grams of potassium. All right, we're going to do one more. How many copper atoms are in a 4-gram sample of copper wire? All right, so it's asking how many atoms. So we need Avogadro's number. And of course, it's asking how many. So Avogadro's number is going on the top because it's asking about the atoms. It's telling us mass, so the mass goes on the bottom. Oh, this is a long one. We'll skip this. We're converting to moles, then finding atoms. All right, so then we take this, okay, this is a 2-step and it's a little bit advanced. I'm gonna skip this for now, all right. All right, they just did a 2-step, if you saw that, but I don't want you to worry about that just yet. That's a little overwhelming, I think. So what I want you to focus on is this. To be successful in stoichiometry, what do we always need? All right, so that's your first question, right? And we always need a conversion factor. And if you're converting from moles to mass, okay, whenever you see mass, what chart do you use? Well, you're going to use the periodic table. So there's your question and answer for your quiz question for watching the video. So if you have any questions, by all means, please let me know. This is a little tricky, but we'll get used to it.